Shells and subshells and orbitals. This discussion is going to talk about where electrons kind of live in an atom. We're going to start with shells and subshells. Electrons live in shells that are outside of the nucleus. They surround the nucleus. Consecutive shells go further and further away from the nucleus. They get larger and larger. They're represented with numbers. So there's a first shell, which is the closest to the nucleus, and a second shell, which is further from the nucleus, followed by a third shell, etc. Within each shell are what are called subshells, and these subshells have letter designations, lowercase letters, that stand for a word. I don't really care that you know what the word is. I'm not even sure I remember what the words are. S is something, spherical, simple. P, I think, stands for principal. D stands for diffuse, I believe, and F stands for fundamental. Although I could be totally off, I'm not even sure I remember what those letters stand for, which is crazy, but that's the way it is. The subshells present will depend on the shell itself, and so the first shell only contains an S subshell. The second shell will contain an S subshell, will also contain a P subshell. The third shell contains S, P, and D, and the fourth shell contains S, P, D, and F. Now there are other subshells, but we don't really talk about them because ground state atoms do not have electrons in anything beyond an F subshell. So the atom would have to be in an excited state, and so we tend to not talk about subshells beyond F. So let's talk about the S subshell. The S subshell, every shell has at least an S subshell. It has if it's the first shell, then the S subshell is called the 1s. And the second shell's S subshell would be called 2s, and the third one would be 3s. As you can see in the picture, the shells get larger. As I mentioned before, the 1s is the smallest. It's the closest to the nucleus, and then the 2s is outside of that, further from the nucleus, and the 3s is outside of that. They differ in size and therefore distance from the nucleus, and they differ in energy. So the first shell is the lowest in energy, and the energy increases as you get higher shell numbers. Now if we talk about P subshells, only the first shell does not have a P subshell. All of the others do. Now within each P subshell are what are called three different orbitals. Now an orbital is really the true home of the electron. Each orbital can house as many as 2 electrons, and what you see here are the 3 different p orbitals. One is aligned along the z-axis, and so that would be called p sub z. The one in the middle is aligned along the x-axis, and that's called p sub x. And the other one is aligned along the y-axis, and that one's called p sub y. And you can see that it's kind of this weird dumbbell shape, and we call those two sort of ends of the dumbbell the 2 lobes. And so basically they represent the area where an electron may be found. This is an image from the book, and you can see there are different colors shown here. The colors actually represent different phases. One is a positive phase and the other is a negative phase. We're not really going to talk about phases of these orbitals, but the colors aren't just because they look pretty. They do mean something. So one lobe is one phase and the other lobe is the other phase, and I don't really care that you know that. The nodal plane is where you have no probability of finding an electron, and we're not really going to talk about nodal planes either, but I thought I would show the picture from the book. These are the 5 different d orbitals. I'm sorry, yeah, d orbitals, and so an S subshell only has 1 orbital, a P subshell has 3, but a D subshell contains 5 different d orbitals. And so you can see those here. The A, B, C, D, and E represent d orbitals. The last one, F, is an F orbital. That's why there are 6 of them shown there. And the purpose of this is just to show you that d orbitals are more complicated. I don't really care that you know what d orbitals look like. I do want you to know that s orbitals are spherical and that the p orbitals have that dumbbell shape. But the d orbitals, I don't really care that you know what they resemble, you can see that they're a little more complicated and they're not all the same like the p orbitals are. They also have colors that do represent different phases, but I'm not going to ask you anything about that either. But I do want you to know that there are 5 of them. So there are 5 d orbitals, and then there are 7 f orbitals, and you can see here the 7 f orbitals. I found this picture on the web. This wasn't from your book. And again, the different colors are significant. I don't care that you know what the f orbitals look like. They're more complicated than the d orbitals, of course, but I do want you to know that there are 7. But we're going to talk about how you're going to know that from the periodic table, so we'll just hold off on that for a minute. Now, this diagram is called an orbital diagram, and it shows boxes that represent each orbital that are present in an atom. And so each of those boxes is an orbital, and you can see the different shells are separated. You know, the first shell is at the bottom, and the second shell is next, and the third shell, and they're separated by energy. Energy is on the vertical axis, so the 1s is shown at the bottom because that's the lowest in energy. The 4p is at the top because that one's the highest in energy. So this little bracket here is supposed to represent the entire second shell, and it contains an s subshell that has a single box for a 2s orbital, and then there's a 2p subshell that has 3 boxes, which represents the 3 different 2p orbitals, 2px, 2py, and 2pz. The first shell, n equal 1, contains only 1 orbital and 1 subshell. Now, this entire area outlined in red represents the second shell, and then this whole set of 3 boxes would represent the 2p subshell. One of the boxes is an orbital, and then if we put electrons inside, right, they're represented by arrows. One of these arrows would be the electron inside the orbital, which is inside the subshell, which is inside the second shell. Now the arrows that represent electrons, we use arrows because electrons have what's called spin. One of them in the orbital will spin in one direction, and the other electron in the same orbital will have opposite spin. So we use the arrows to indicate that we know they're spinning in opposite directions. We're going to continue the discussion of orbitals and shells and all of that by a discussion with a discussion on quantum numbers. Quantum numbers are kind of abstract, but this is really just, they're numbers that are used to describe the shell and the subshell and the orbital to which an electron belongs. First, we're going to talk about the different kinds of quantum numbers. Principal quantum number is abbreviated lowercase n. This designates the shell number. This is going to be any integer that starts with 1, so 1, 2, 3, 4, 5, 6, 7. It increases indefinitely. All of the elements that are known at this time in their ground state would have an n of 7 or lower. However, n can be higher for elements that of course have not been created yet, or for excited states. So that's what that statement is telling you there. The maximum value is 7 for elements known to the ground state. The second quantum number is the lowercase l abbreviation, and it is the azimuthal quantum number. This designates the subshell, and so they're just set integers associated with each subshell. The possible values will depend on the value for n, and so L could be any value starting at 0, increasing by integers 0, 1, 2, and it goes up to n minus 1. And so therefore, if n is 4, the maximum value for L would be 3. The magnetic quantum number is m sub L, and this designates the actual orbital itself, and this number, the possible values for this will depend on L. So m sub L will vary from negative L up until positive L, and so this is going to be integer values. So let's say L is 2, that means that m sub L starts at negative 2, and it can be anything from negative 2 up to positive 2. So it would be negative 2, negative 1, 0, 1, or 2. So there are several different possible values. These are the different, this is a table 2.2 from your book, that gives the n or shell number, and then L, the azimuthal quantum number, and m sub L, the magnetic quantum number. And you can see in this table that if n is 1, then L must be 0, because L starts at 0 and goes up to n minus 1, which means that if n is 1, L can only be 0. And if L is 0, m sub L can only be 0 as well. And so the in value means the first shell. 0 represents the subshell of S, and so that means that's the 1s subshell. There's only one orbital in the subshell, and that's because there's only one value listed for m sub l. Now if we look at a specific example here, the third shell can have a 3s or a 3p or a 3d subshell. So that's represented by L of 0 or an L of 1 or an L of 2. There are 5 values listed there for m sub l when n is 3 and L is 2. So I circled those in green. So what that means is that for a 3d subshell, 3 because n is 3, d because L is 2, that means for a 3D subshell there are 5 possible values for m sub l, which means there are 5 orbitals. That's why there are 5 orbitals, is because there are 5 possible magnetic quantum numbers. Now the last value is the spin quantum number, which is m sub s. This designates the electron within, this designates the actual electron, and it's either plus 1/2 or minus 1/2 depending on its spin, if it's up or down. Now, so one of these is plus 1/2 and one of them is minus 1/2. This is why, again, why we draw electrons as arrows in our orbital diagrams. Now we're going to do some practice on quantum numbers, and hopefully that will clarify some things. We're going to be doing some practice with quantum numbers. Since they're so abstract, it's a good idea to practice these. So here are the practice problems. What type of subshell, 1s, 2, 3p, etc. So you're supposed to give the subshell designation, is represented by each of the following quantum numbers, and for each one, how many orbitals are present in that subshell. So let's use our examples here. So we have n equal 5. That means it's in the 5th shell. And L is 3. For L of 3, that means it's an F subshell. So this is a 5F subshell. So that's the answer to the first part. F subshells can have 7 orbitals. Any F subshell has 7 orbitals. That's the answer to the second part. Part B, n equal 2 means it's in the second shell. L of 0 means it's an S subshell, so it's 2s is the orbital designation. S subshells have 1 orbital in them. That's always true. N equal 4 means it's the 4th shell. L equal 1 means it's a p orbital, so that's a 4p orbital. P subshells always have 3 orbitals. So there are 3 orbitals housed in any p orbital, any p subshell. Since quantum numbers are so abstract, I think it's probably a good idea to practice these. So we're going to do some practice problems. Let's start with number 1. What type of subshell is represented by each of the following quantum numbers? And for each, how many orbitals are present? So we'll do part A. N equal 5 means it's the 5th shell. So our orbital designation is going to start with a 5. L equal 3 represents an F subshell. So the orbital designation, this type of subshell, is 5F. And F subshells always have 7 orbitals. So it's a 5F type of subshell. And the answer to the second part, how many orbitals? It has 7. Number 2, part B. N equal 2 means it's the second shell. L equals 0 means it's an S subshell. So that means this is a 2s subshell, which was going to contain 1 orbital, as all S subshells do. Part C, N equal 4, that's the 4th shell. L equal 1 is a P subshell. So this is a 4p subshell, and p subshells always contain 3 orbitals. Part 2, If L equals 4, then what can you deduce about N? Well, we know that L depends on N, that L starts at 0 and can go all the way up to N minus 1. So based on the fact that L equals 4, then that tells you something about N. That tells you that N has to be at least a 5, right? So I don't know if that makes sense, but you can always go backwards in your head and say, well, if N is 0, or if N is 1, L can't be 4. If N is 2, L can't be 4. If N is 3, L can't be 4. So L can only be 4 for values that at least start at 5. If N is 5, that means that L can be 0, 1, 2, 3, or 4. So N has to be at least 5 to get an L of 4. If M sub L is plus 2, then what can you deduce about L? So the same idea here. The identity, the quantity L will determine what M sub L is. And so based on what M sub L you have, you can figure out, sorry, I guess I forgot I wrote all those other things, 5, 6, 7, it can be anything greater, 5 or greater. So the second part, if M sub L is plus 2, what can you deduce about L? M sub L depends on L. So M sub L is going to vary from whatever negative L value you have up to a positive L value. So if M sub L is plus 2, then you know that L can be 2. You know L could be 3. You know L could be 4. But L could not be 1. So if L was 1, then you'd only have negative 1, 0, and 1. So L has to be at least 2. It can be 2 or 3 or 4. Now, if we keep going, number 3, which of the following sets of quantum numbers are allowed? This is probably the most important kind of question you're going to answer, the most common kind. Allowed just means it follows the rules that I gave you. So if we look at each one, remember the rules are that, N is an integer, starting at 1, that L it depends on N, and then M sub L depends on L, and M sub S has to be plus or minus 1/2. So based on these rules, we're going to decide which ones follow the rules and which ones do not. So for part A, we're going to say, okay, let's look at number 4. Is 4, does that fit the rules? Yes. Does 3 fit the rules? Well, 3 depends on 4, and that's okay, because if N is 4, that means that L can be 0, 1, 2, or 3. 3 is N minus 1, right? So 3 is on our list, so that's okay. Negative 2, for an L of 3, then M sub L is going to be anything from negative 3 to positive 3. So negative 2 fits in that list. It's in there, so that's okay. And then the last quantum number is fine, plus 1/2. So A is good. So we'll circle that one. Part B, I'm going to go on one at a time. So the first one here, N is 2, that's fine. And if N is 2, that means L can be 0 or 1, but it can't be 2. And so that first one, that part B, the L quantum number can't be true. So this is wrong. And therefore you would not circle that one. Once you get to one that's wrong, you just move on. You say that one can't be true. Part C, N is 3 is fine. And if N is 3, that means L can be 0, 1, or 2. And 2 is on that list, so that's fine. M sub L depends on L. And therefore, if L is 2, M sub L can be anything from negative 2 to positive 2. Negative 2 is on that list, so that's okay. And plus 1/2 is fine, so we're going to circle C because it's fine. Part D, 2 is fine. If N is 2, then L can be 0 or 1, and that's 0 is on our list, so that's fine. However, for an L of 0, M sub L can only be 0. It can't actually be 1, and so that one is wrong. So you're not going to circle D because of that M sub L value being wrong. Part E, N of 7 is fine. L can be anything from 0 up to 6, and 5 is on that list, so that's fine. For an L of 5, M sub L needs to be anything from -5 to +5. -4 is on that list, so that's fine. And +1/2 is good, so we're going to circle E as well. Now, give all allowable combinations of quantum numbers for an electron in a 4D orbital. So a 4D orbital means N is 4 and L is 2. Those quantum numbers are set because of the 4, and then the L is 2 because of the D. So that means that for L of 2, M sub L can be -2, -1, 0, 1, or 2. And M sub S can be plus or minus 1/2. So that's going to give us 10 different combinations. For all 10 combinations, the 4 and the 2 are set because it's a 4D orbital. So 4 has to be there and the 2 has to be there because that designates a 4D subshell. However, the M sub L value will vary for all the possible ones it can be. And then the M sub S value will vary between +1/2 and -1/2. So here we have M sub L of -2 and the M sub L of -1, M sub L of 0, M sub L of +1, and M sub L of +2. So those are the 10 values. And these 10 values, there are 10 because there are 10 possible electrons. There are 5D orbitals, and each one can house 2 electrons. So you should get 10. Also, if you look at the periodic table for that section of the periodic table, right, 4D, right, for the 4D section, if you look here, there are 10 boxes or elements in that section. And so since there are 10 elements in that section, each box kind of represents where, you know, the space that an electron fills in as you increase the size of these atoms, right? So 10 boxes means 10 electrons because 5 orbitals. That's why we get 10 sets of quantum numbers.